Let's see. And the first speaker of the day is Seyoung Jeon. Maybe you can share your screen. And he will talk about the star formation quenching and the transition epoch of the Horizon AGN galaxy. So please go ahead, and I will interrupt you and say 3 minutes when you have 3 minutes left. Okay.
Thank you for the introduction and greetings. Hi, I am Seyoung, a student working with Seogyun at Yonsei University. I'm glad to talk about my recent work. Today's topic is the star formation quenching and the transition epoch of the Horizon AGN galaxies. The galaxy cluster is a very unusual environment. Galaxies residing in the cluster of earlier type were quenched, older and redder than built galaxies. Cluster galaxies are quenched now, but it does not guarantee that they have always been quenched than built galaxies. To clarify this, we should examine the star formation history with overcoming the limit of the observation. With cosmological simulation, I calculate the quenching timescale using the parameterized star formation history, and then I determine how quenching timescale varies. Finally, I examine when cluster galaxies became less star forming than filled galaxies. I use cosmological hydrodynamic simulation data, Horizon AGN. Horizon AGN used WMF7 cosmology, and the length of the site is about 140 megaparsec. Also, mass resolution and spatial resolutions are here. Horizon AGN reproduce the observation well, like cosmic star formation history, luminosity function, or CMD. This is the history of cosmic star formation rate density. The result of Horizon AGN in the red line is well matched to shaded observation result. For safety, I use galaxies with more than 10 to the 9 solar mass, corresponding to about 300 solar particles. I define the cluster and group halo for mass cut of 13 and 14. And then I classify cell-like galaxies using potential criterion. There are about 13,000 galaxies in group and clusters in Horizon AGN. These are star formation histories of galaxies with different mass range. Red and green lines are cluster and group galaxies, and the blue line is filled galaxies. Because of the additional mesh refinement at scale factor of 0.1248, there are star formation bumps. This phenomenon is prominent in low-resolution simulation. First, the left is lower mass galaxy case. You can see a clear environment dependency. Cluster galaxies were more star forming than filled galaxies in early universe, and then quenched rapidly. However, right massive galaxies, there is no difference between cluster, group, and filled galaxies. Moreover, the shape of the graph is narrower than low mass case. I talk about quenching timescale using star formation history first, and then move on to the transition epoch between cluster and filled galaxies. To remove stochastic features, the first to do is fitting the star formation history with the model. I chose the exponential decay model, namely delayed tau model. There are three parameters. First, tau. Tau means the quenching timescale, which is the most important parameter for today's talk. Higher tau means extended star formation, and smaller taus means rapid quenching. A is the amplitude of star formation history, and T0 is delayed time. I applied this fitting to all sample galaxies and found some trends. The top panel shows the distribution of tau for different stellar mass bins of field galaxies. The red line is massive galaxies, and the blue line is low mass galaxies. For field galaxies, more massive galaxies have smaller tau values, which means they have experienced rapid quenching and is well matched to the expectation of observation. Next, the bottom panel shows the tau difference of field and cluster galaxies. And negative delta tau means those cluster galaxies have smaller taus so that they have experienced more rapid quenching than field galaxies in each mass bin. First, low mass galaxies of blue line have smaller tau values than field galaxies, and in more massive host halo, tau is decreased much more. Therefore, low mass galaxies seem to be influenced by environmental quenching strongly. Second, if a stellar mass is increased compared to the host mass, tau approaches to field's value, which means they are getting to have the resistance to the environmental quenching. Last, most massive galaxies of red line do not show any difference. They might not be affected by the host environments, but quenched by an internal process like agent feedback. So far, it's clear that both stellar mass and host mass are highly related to the quenching timescale. Then let's think about one situation. Two galaxy populations have similar stellar mass and live in the same cluster halo. But one galaxy lives in that environment for a long time, whereas the other galaxy just came in. It's natural to think that they have experienced a different amount of environmental effects. So I check one more thing, time since info. It means how long galaxies live in the host halo. Here's the result. The left panel shows galaxies with lower TSI, so recent infallers, and the right panel shows ancient infallers having longer TSI. For recent infallers, their tau values still close to field galaxies, especially for massive satellites of low mass halos, because they don't have enough time to be affected by dense environments. On the other hand, ancient infallers show significant tau drop. Of course, in the most massive clusters, most satellites have lower tau values, even for the recent infallers. However, overall drop of tau is substantially affected by TSI. Thus, residing time is comparable parameter to stellar mass or host mass for the quenching timescale. To sum up, low mass satellites which live in massive cluster a long time have very small quenching timescale compared to field galaxies. Then it's natural to expect that there was an epoch when cluster galaxies had formed more stars than field galaxies and then reversed. I call it the transition epoch. For a similar mass range, cluster galaxies were start forming and then quenched rapidly at the early time due to lower quenching timescale. The transition epoch is expected about redshift 1. However, whether it does exist or is universal for all environments is controversial. If cluster and field galaxies have similar star formation histories, we cannot define the transition epoch because there is no transition. So I measure this transition epoch with different stellar mass and host mass bins. This is the result for cell-like galaxies. Horizontal axis is post-halo mass, and the vertical axis is stellar mass of cell-like galaxies. Large symbol size means transition does not exist. Sorry. Large symbol size means transition does exist. And small size means no transition. And the redder color is the earlier transition, and the bluer color is the later transition. First, low mass satellites show a clear trend. They became quiescent earlier in massive halos, about 8 gigayear ago. In the small groups, the transition epoch is later, about 6 gigayear ago. In the massive cluster, low mass satellites have an earlier transition epoch, which means there might be a strong environmental effect for lower stellar mass. The transition epoch goes to later time as stellar mass increased. And finally, most massive galaxies do not show the transition. If galaxies have relatively higher stellar mass compared to their host mass, there is no transition. Probably, they have a resistance to environmental quenching so that they have similar star formation history as field galaxies. So the transition epoch of group or cluster galaxies is not universal, but can be varied by both stellar mass and environments. Let's wrap this up. I examined the star formation histories of cluster and field galaxies using Horizon AGN. When we see the quantum timescale and the transition epoch, it's important not only how dense environments, but also how long-lived in dense environments. And cluster galaxies became quiescent earlier in massive cluster, especially for low mass satellites. And this phenomenon is prominent if they fall in denser environments all the time. However, if group or cluster galaxies are massive enough or very recent infallers, it means lower TSI, their star formation histories are not different from the field star formation histories. Okay, that is my summary, and thank you for the listening, and that's all.
All right, thank you very much for this talk. Any question for Seyoung? Let me see this. While I wait for some more questions, I have one to ask. Well, maybe Joachim can go first, and I will go second.
Thank you for the talk. So, since the quenching is very rapid, does that mean that these galaxies are stripped by Ram pressure stripping, or is it more what is called strangulation that's going on?
I missed your point.
Sorry, could you did you not get the question?
I missed your point.
Yeah, so you said that the quenching is rapid. So what is the process of quenching? Are they stripped of their gas, or do they keep their gas and just slowly die off? I guess since it's rapid quenching, it's the former, or what?
What I did is more statistical approach, and I didn't see the detailed process of quenching. So I'm not sure, but as you mentioned, Ram pressure stripping in cluster environments will be candidate for this quantum process, rapid quantum process.
Okay.
Okay, Jeremy.
Yes, thank you for the very nice talk. I have two naive questions. The first one is about the satellite galaxies. I think I recall some simulations where satellite galaxies tend to turn red too quickly in cluster environments. I was wondering, so you find that they become quiescent first. Is it actually a problem, or do your satellite galaxies have colors or properties that are comparable to observations? This is the first question. And the second question was I was wondering about this transition time that you are looking at. You seem to find different times at different halo masses, but the different halo masses have different histories. So I'm wondering, is there a mass, a transition in mass, which is more natural than a transition in time? That's a more vague question. I don't know if you can comment on these points.
First, for your second question, yes, there. I think so. There was mass transition, but when this star mass is final mass and statistically, final mass is also related to mass at the transition. So I think the mass transition can be separated to this star formation quenching. And sorry, what was your first question? Sorry.
Yeah, maybe the first question, this was just a general comment. Maybe the first question is more straightforward. Did you compare the properties of your satellite galaxies to observations in terms of colors, and do the satellites survive long enough in your simulation? That was my first question. Do they form stars long enough, or are they quiescent too quickly?
The separation rate for other things at redshift 0 of satellite galaxies are well matched to observation, but in observation, star formation history is very uncertain, so I cannot compare those. Yes.
Okay, thank you.
Okay, then I will sneak in a question as well. So you're using Horizon AGN for this. In order to understand the role of AGN feedback, have you thought about just doing the same analysis on just the regular Horizon simulation and see how they differ?
You mean Horizon low AGN simulation?
Yes, yeah, because I guess the role of AGN in relation to the environment is I guess it will be interesting to try to separate, right? So which effect is doing what here, and then it would be useful then to have a simulation without AGN to understand what actually happens in terms of the quenching timescales. And I think and you have the Horizon simulation, I guess, that does not have AGN in it. So maybe that's more of a comment then that would be useful to have a look at this simulation as well and just apply the same pipeline. Yeah.
Actually, I didn't check the just Horizon simulation because is cannot reproduce the observational constraints, so I didn't check it. But I think it will be good comparison to use them. Yes, thank you.
Okay, great. So do we have any final quick question? If not, thanks again for the talk. We'll move on to the next speaker, Jaekyoung Jang. Please share your. Let's see. You are unmuted now, I think. Yeah, or should I? Okay. Good. Okay, next speaker, Jaekyoung Jang, talking about New Horizon, the galaxy structure, decomposition, photometry versus kinematics. So please go ahead.
Okay. Hi, my name is Jaekyoung Jang and Jaehyun Jang, the master student of Yonsei University and working with Seyoung Lee. Today, I will present the comparison between the photometric and kinematic decomposition result in New Horizon. Here are beautiful pictures of galaxies. We can see the weak signal of the disk on the left galaxy and a clear spiral on the right galaxy. However, without the spectroscopical measurement, this light information is all we have got from the galaxy. We cannot know the detailed information of the galaxy structure or the kinematics from this observation directly. So in the photometrical approach, observers typically try to define the galaxy's morphology with some empirically well-matched mathematical model. The most famous and excellent model for this is the Cersei profile. Like the lower panel of the figure, we fit the galaxy with the 1D or 2D radial surface brightness fitting and measure the amount of the bulge, disk, or other components. However, when we deal with the galaxy using simulation, the kinematic information is fully provided. So we can use almost every intrinsic information of galaxies. Typically, we measure the disk and spheroidal components of the galaxy by using some parameters like this V over sigma or K rotation or a circularity parameter, which is suggested by Abadi et al. 2003. Or some case, the spin parameter can be helpful. There can be 1,000. This is, of course, an exaggeration, but a lot of ways to define the disk component and others. However, when we are trying to bind these two pieces of information, the photometric D2T and kinematic D2T, there's a massive gap between these arise. This is the figure from Schianapisco et al. 2010, who tried to compare the photometric and kinematic D2T using simulated galaxy with a mock image with the Cersei profile fitting and kinematical decomposition using circularity parameter. We can see that there is a considerable gap between them. The gap is about 0.3 and 2.6. So there's a much difference between the observation and the simulation when we are measuring the D2T or B2T. So this is why I am trying to figure out how much the difference is between them. So I tried to measure D2T in observer's view and with kinematics using New Horizon simulation. New Horizon is a high-resolution hydrodynamic cosmological simulation, and the minimum spatial resolution is about 40 parsec, and for stellar mass, about 10 to the 4 solar mass. And this high resolution is ideal to compare these. So now I am going to introduce the methodology about the mock imaging and two different ways to decompose the galaxy. First, I applied dust extinction using the skirt pipeline, the post-processing code that can mock the radiative transfer. The sample galaxy is at the redshift about 0.17, and I used the galaxies with stellar mass more than 10 to the 9.5 solar mass, of course, without the ongoing merger. And the mock image's pixel scale is about 40 parsec per pixel. And I convolved the image with the Gaussian filter with the width about 2 pixels to degrade the image to consider the seeing effect. But I didn't apply the sky background noise because this is very arbitrary and different for various observational conditions. And for kinetic decomposition, I use 3 parameters. First, the circularity parameter, and second, the remaining angular momentum parameter, and third, the specific binding energy. I assume the spherically average potential calculated with every stellar DM particle and gas cell inside 10 effective radius. The under figure shows the phase space with these three parameters. I also used GMM, the Gaussian mixture model, an unsupervised machine learning technique for clustering. This methodology has been used for several years, and in the most recent case, Mindu is trying to find the intrinsic structure of illustrious TNG 150 using this technique. However, the problem is that the total number of clusters is the input parameter. So this technique itself cannot provide the total number of intrinsic structures of the galaxy. So I just set the total cluster number as 15, which is large enough to cluster every single detailed structure of the galaxy in the phase space. So the under figure is one of the results. And with each cluster's central position, I divided this spheroidal component or this component of the galaxy with circularity cut about 0.5. The result is on the left, right. In the upper panel, the histogram of the circularity parameter, you can see that the most random component of the galaxy is picked at about 0.0 or 0.1, and this component with a sharp peak at 1. This is an expected result. And also, the GMM technique provides a smooth transition between the spheroidal and this component at the circularity cut. The interesting thing is that there are some peaks of spheroidal component in the specific energy parameter. And the morphology of these three components seems to show the core or bulged component and bulge or halo component plus some major remnant component. So this is very interesting result, and GMM might be very useful to study the evolutionary past of the galaxy. And for photometric decomposition, I used MCMC to fit the profile. I only used the pixels with the minimum pixel resolution and R90. And also give some magnitude cut with G-band surface brightness under 26.5, and the fitting is done with R-band luminosity. I fixed the Cersei Index as 1. For multi-component fitting, I try to apply 1, 2, and 3 component fitting. And to find the optimal fitting result, I used BIC, the Bayesian information criterion, which is based on chi-square, but also penalized by the number of used parameters. So the right is the result. So now the results. First, the D2T kinematic versus stellar mass. So D2T kinematic versus stellar mass has shown like this. You can see that there are few elliptical galaxies. Let me show you the with pointers. Okay, sorry. This is spoiler. Okay. So you can see that there is a few elliptical galaxies with the higher mass region. And also the V over sigma and D2T kinematics shows a good agreement with a smooth transition. And the next is the color versus magnitude diagram. The flux is measured after applying the extinction, and the line of the figure is suggested by Gaboret et al. 2010 to distinguish the early and late type galaxies. When I color the point with the kinematic D2T, generally the overall distribution with the disk and random dominated galaxy follows this cut very smoothly. But of course, there is some exception, but smooth transition is observed. And next, the concentration versus the Cersei Index. We found that some linear trend, linear increasing trend at the lower Cersei Index region, but with large Cersei Index, this kind of linear correlation is removed. So this kind of large spiral galaxies has some dense core, This makes the Cersei component to be increased, but the concentration parameter is remain constant. This means that the innermost component makes a very high slope, but the general distribution of this galaxy is very different from the innermost component. So there is some discrepancy. Also, I measured the asymmetry or clumpiness using particle inside R90. The distribution between disk or random dominated galaxies is colored with blue and red. And this shows some difference, the statistical difference, but there is some considerable overlapped region. So this plane is hard to find the intrinsic structure property precisely. And this is the D2T photometric versus D2T kinematic. The y-axis is the photometrically measured D2T, and the x-axis for kinematical way. The red line shows a diagonal line. We can see that there is many galaxies with a single component fitting result. This kind of single component result, or the difference, is very much more worse at the lower stellar mass region. So for the galaxies with stellar mass under 10 to the 10 solar mass, there's the single component galaxies the most dominant ones. But in the massive galaxies, we find some slope. We find some linear correlation with slope about 1, but the y-intercept is about 0.11. Also, there is some single component, but others follows this kind of correlation.
You have 3 more minutes.
Okay, thank you. When I check the single component galaxies, first the case 1 pure disk-like galaxies. You can see that morphologically, we see no significant feature of bulge in this kind of galaxies. But when we kinematically decompose, there also exists a spheroidal component in the inner part of the galaxy. Moreover, this component shows the linear-like distribution in the inner component with different slope, and also the disk shows some linear slope, linear distribution with different slope. So this kind of galaxies seems to have a relatively more rotationally supported and flat dispersed spheroidal component, and these components cannot be resolved by photometrical fitting. So there is no way to measure the spheroidal component by fitting the profile, because I used 1, 2, and 3 component profile to find the optimal profile fitting. And also, unless these components is fully settled down, you can see that the circularity histogram, the peak is about 0.6. So this component, if this component is fully settled down, neither the profile fitting nor the kinematics can successfully resolve the disk component. The radial profile only shows a single exponential-like component, and the circularity parameter cut, the 0.5, as I fixed, is inadequate because the disk component does not exist, but has not yet peaked around 1. So this mainly occurs in the region with kinematic D2T between 0.3 to 0.6. And the last pure spheroidal component-like. On this region, there can be some embedded disk component, but this signal is too low, so this component cannot be resolved using Cersei profile fitting. The concentration index might be helpful to divide disk and spheroidal likeness of one component galaxies. You can see that the color is the concentration, and color is very different from disk-like and spheroidal-like. So this is the summary. I used the new rising galaxies with stellar mass over the 10 to the 9.5 solar mass at the redshift 0.717 and mock imaging using SCIRT pipeline. The result is photometric decomposition result does not mean the intrinsic kinematic structure for many of galaxies. A large amount of one component galaxies shown, and this kind of a trend is large at the lower mass. And CAS diagram also does not work well. So galaxies with multi-component shows slope about 1 and y-intercept is 0.11. So there is some gap for this kind of component, but there is still very many cases of one component fitting. So is V over sigma is the best parameter to measure the D2T? I think so. So this is the V over sigma versus D2T kinematic. So maybe precise measurement for galaxy structure essentially need spectroscopy more than the photometric way. Thank you for your listening.
All right, thank you very much. Questions? Let's see, I don't see any hands up for now. Maybe I can sneak one in then while people are thinking. I was first going to ask you about how you account for the contribution from bars, but then I also realized that I believe there are no bars in the New Horizon simulation, right? Or do you actually find that you can actually account for a larger bar fraction by doing it in the way you are decomposing your galaxies here?
Yeah, right. And if there is a bar, then this kind of complexity will increases. But with GMM technique, the bar component can be classified as a spheroidal component. Yeah. So the existence of bar is not much big problem on my project.
Yep. Okay, any other questions? Okay, if not, then we can move on to the next speaker. Thanks a lot for the talk. So then Sanhan, maybe you can share your screen. Thank you. And Sanhan will talk about the velocity dispersion profiles of New Horizon galaxies. Okay, go ahead.
Thank you. So, good morning, everyone. My name is Sanhan, and I'm a PhD student in Yonsei University working with Seyoung Jeon. Today, I'm going to talk about the ongoing project about the velocity dispersion profiles of New Horizon galaxies. So the velocity dispersion is one of the basic properties of galaxies. In traditional spectroscopy, it was measured by integrating light within certain radius. In this case, what you can actually measure is not the velocity dispersion itself, not only the velocity dispersion itself, but also the velocity gradient of the Burke rotational component. So these two properties cannot be easily separated for this kind of spectroscopy. But integral field spectroscopy kind of elevates this problem with using multiple spark cells with smaller beam size. You can now measure the velocity dispersion profiles, or sigma profiles, we call. Before we go into the detail, let me ask you one question. What shape would you expect if you measure the radial sigma profile? So in function of the radius from the center, what would you expect as the velocity dispersion profile? One is rising, the second option is falling, and the third is falling and rising. In fact, all these cases what you can actually find in the real universe. There are a variety of sigma profiles for galaxies, but more interesting fact is they all look similar when you look them by eye. So what made them to have such different shape? Perhaps it is linked to the assembly history of galaxies, such as how much this galaxy experienced accretion or mergers or star formation. If we could find these various shapes of sigma profile from the simulation, it would be wonderful. So we can use the strength of the simulation, then we can use the strength of the simulation to trace what happened to those galaxies. In this study, we used New Horizon. It is well known, as Jaekyoung introduced. It has a very good spatial resolution and redshift. It finished at redshift about 0.17, which is a perfect sample to study the internal kinematic evolution of galaxies. It has galaxies up to 10 to the 11.4 solar mass. From New Horizon, we selected a sample of galaxies with mass above 10 to the 9 solar mass. And we extracted galaxies from 18 uniformly timed snapshots, ranges from 0.17 to 2.15. And then we defined boundary of each galaxies as the radius where R-band surface brightness drops fainter than 26.5 magnitude per arc second squared. And then we divided stars for each galaxy using spherical shells to measure the sigma of galaxy in function of the radius. To minimize the effect from bulk rotation, we used 3 directions for measuring sigma in spherical coordinates: radial and theta and phi. So here's what we got. Lines on the left panel are the sigma profiles in New Horizon. We found a variety of profiles in simulated galaxies, just like the observation. And we have some galaxies with falling profiles. And we also have some galaxies with rising profile inside the effective radius. And we also have rising profiles outside the effective radius. From this, we fitted each sigma curve to the broken power law shown here. So the panel on the right shows the result of the fitting, which looks nice. And then we extracted 2 parameters, gamma inner and gamma outer, from the fitted power law function. They are defined as the slope measured in 0.4 R50 and 4 R50 in log-log plane. And this plot shows the comparison of gamma inner and gamma outer with the observation. For the left panel, our result largely agrees with semi-observation, which includes both ETGs and LTGs. But you can see the trend inverts as you go to the more massive surveys. Although they only include massive ETGs, and most of the New Horizon galaxies are LTGs, as Jaekyoung showed before. And the right panel shows the sigma slopes on the outskirts of the galaxies. And you can see the steadily increasing trend, which is nicely extended to the observational trend. The plot I'm going to show you from now on is the radial sigma profile as the median curve of many galaxies. In this slide, I'm showing the sigma profiles of galaxies with different masses in each color and different redshift in each panel. As we go to the more massive galaxies, slopes on the inner parts of the sigma profile become steeper, and slopes on the outskirts become shallower. And this is what we already seen from the previous slides. And we can also find that there is no strong changes between each panel, which means we can effectively rule out the redshift bias when we compare galaxies came from different snapshots. So what makes galaxy sigma profiles to change? To figure out this, we trace back the origin of each star in the galaxy and classify them depending on where they came from. One is in-situ formed stars, which are the stars that were formed in the current galaxy. And the other is the ex-situ stars. They are formed outside of the galaxy and later inferred through merger or accretion. We mark them as accreted here. As you see in the figure, accreted stars generally have higher velocity dispersion than in-situ formed stars, which is expected because in theory they tend to have they tend to keep their kinetic energy when they first came into the galaxy. To look at the effect of the accretion in more detail, we divided galaxy samples depending on their fraction of accreted stars, which is F accreted. And they are shown as different color-coded lines. The bottom panels indicate the accretion fraction in function of the radius. You can see accreted stars are generally distributed on the outskirts. When you look at the intermediate mass range, where we have a good statistics for each color-coded lines, you can now see the general trend of the accretion, general effect of the accretion on the sigma shapes of the sigma profile. From previous slide, we found accreted stars generally have higher velocity dispersion. So if you have those stars in the region, the velocity dispersion will be enhanced, and the effect becomes stronger on the outskirts as we have more and more accreted stars. It makes sigma profiles to shift toward the positive slope, and with the radius, making it shallower and flatter. To look at the effect of the accretion in more general, we brought the plot I showed already from the previous slide, but it is a plot of gamma outer versus stellar mass. In this case, we color-coded each point depending on the accretion fraction, and we can clearly see the effect of the accretion as a key factor that decides outer sigma slope. As galaxies accrete more stars, they tend to have shallower slopes on the outskirts. And also, we can say that because more massive galaxies generally have higher accretion fraction, their gamma outer is larger in average, and possibly they might even show a rising profile in more massive populations. But stellar accretion is not the only effect that changes the shape of the sigma profile. We also looked into the dynamic revolution of in-situ formed stars. In this slide, we divided in-situ formed stars into two groups according to their age, old and young stars. The dashed dotted line here shows young newly formed stars, and their velocity dispersion is a lot smaller than the old in-situ stars, which is shown as dotted lines. This means the velocity dispersion of newly formed stars are initially very low, following the cold kinematics of gas, but they are enhanced over time by dynamical heating. Bottom panels show how much fraction of mass are occupied by each type of stars in function of the radial distance. Let's look at the massive galaxies first. Central part of these galaxies are mainly occupied by old in-situ stars, which indicates their inside-out formation process. But if you look at, if you look at less massive galaxies, you can see their age gradient is on the opposite direction. Their center is mainly occupied by newly formed stars, and it means these galaxies are still forming stars at the center. And this makes a big difference on the shape of the sigma profiles too, because massive galaxies have old dynamically heated core. Their sigma curve is much steeper at the central region. And the less massive galaxies, because of the newly formed stars, their central sigma is reduced, and they more tend to show flatter sigma profile. And here's my summary. We found a variety of sigma profiles in the New Horizon simulation, and there are basically 3 types of effect that determines the shape of the profile: dynamical heating, star formation, and accretion. In massive galaxies, central region is mainly occupied by old dynamically heated stars, which makes sigma to rise as you go to the inner part. And as you go to the outer part, the contribution of accreted stars also makes sigma profile flatter, and sometimes even make them rises with the radius. As for the less massive galaxies, they normally form stars at the center, which makes a flat or rising central sigma profile, and occasionally outer sigma profile is also enhanced by accretion. And because plenty of time is left, I have a couple of more slides to talk about my future plan. In this talk, I focused on finding physical origin of sigma profile in 3-dimensional distance to measure the sigma profile. But for more direct comparison with the observational constraints, it is essential to make it in similar condition. So we will generate mock IFU images of galaxies to measure sigma profiles in 2-dimensional projection in the future. And there are lots of observational biases that can affect in our analysis. The most prominent one is the effect of the spatial resolution. It is basically composed of 2 effects. The first one is the effect that smooths out the original sigma profile. And it can be represented by applying Gaussian corner, Gaussian convolution to the original sigma profile. And the latter is the velocity gradient term. If the local velocity gradient is higher, then the sigma will be boosted. Sigma at the region will be boosted. To see the impact of the poor resolution, we selected one disk galaxy from New Horizon and simulated the resolution effect in 2 projections, face on and edge on. And this below shows the radial sigma profile of the galaxy in 2 different projections. And you can see the effect of sigma smoothing with lines with different colors. And as the resolution gets poorer, the central sigma slope significantly changed. And I also showed dashed dotted line, which velocity gradient term is removed, and they show no strong difference, which means the sigma smoothing has a strongest impact on the inner sigma, measuring inner sigma slope. So this is what I got so far. Please stay tuned for the upcoming results, and thank you for your attention.
Okay, thank you very much, San. So questions on this talk? Yes, Tewa.
Thank you for nice talks. I have questions so the velocity dispersion profile is somewhat related to the morphological difference of the galaxies. We can check some those difference in mock image or something like that.
Yeah, of course. So in this study, we did not distinguish the LTGs and ETGs, but there should be clearly, I think there should be a morphology bias, because central region is especially the stellar light is dominated by star forming light, newly formed stars. Yeah, so the line here, which shows the opposite trend as in function of mass, I think this partially indicates there could be a difference in sigma profile trend for the low LTGs and ETGs, because the sample I chose from year 2018 only includes ETGs. So yeah, that's an interesting topic.
Okay, I saw Hugo's hand up. Did you want to ask a question or?
Yeah, it was the same if you have a relation, or actually it was slightly different. So if you have this relation between, I mean, you have the velocity dispersion and you fit it with several power law, and I was wondering if you have checked if this power law is somewhat related to the density profile, because you were showing at some point that similar galaxies can have different velocity dispersion profile, and yeah, is it something that you also find in the simulation, or from the density profile, you can say something about the velocity dispersion profile?
Yeah, actually, we found some also dependence on the density profile of the galaxy. For example, if a galaxy is more centrally concentrated, then the sigma profile at the center will rise. But yet we haven't checked them in detail.
So do you think it's vain, I mean, impossible to, from simply observation of the density profile, to have an idea of the velocity dispersion, and we definitely need spectroscopy and IFU, or we can say something even if we have just the observed photometric image?
Yeah, I think the density profile itself defines what the sigma profile of that galaxy will be, because that makes potential of the galaxy in principle. And yeah, we can expect at least something for the density profile of the galaxy. But as you see in this example, you can see their density profile is not very different from each other. I think there should be more like history of that galaxy.
Yeah, but it's very cool that for similar density profiles, then you can say a priori something from the history of the galaxy according to you. So, it was very nice. Thank you very much.
Thank you.
Okay, thank you. I don't see any more hands, so thanks for the talk. Let's go. Oh, Joachim has one. Ooh, last second question.
Hey, it's probably a stupid question. Do you see counter rotations in the simulation? And if so, what do the velocity dispersion profiles look for those?
Yeah, that's an interesting topic. Actually, we did not explicitly searched for counter-rotating galaxies in New Horizon, but I found one galaxy with kinematically decoupled core, and that galaxy showed extra enhancement at the central velocity dispersion due to the shear velocity and in the central region.
Yeah. Okay. Then we'll move on to the next talk. Thanks, San.
Thank you.
So next speaker is Jaehyun Lee. Maybe you can share
hello. Can you hear me? Can you hear me?
Yes.
Okay. So let me share my screen.
We will now hear about simulating jellyfish galaxies, a case study for a gas-rich dwarf galaxy. Okay, please go ahead.
Okay, hello, I'm Jaehyun Lee. Today, I'm going to talk about the formation process of jellyfish galaxies via ram pressure stripping. Ram pressure stripping is a hydrodynamical process that can directly remove the ISM from galaxies, and this is of course, stronger in denser environments. So ram pressure stripping is known to be one of important environment effects. And ram pressure stripped galaxies are characterized by their unique tails, and the tails have been observed in many cluster satellites in H1 or H-alpha bands. Some RPS galaxies even have young stars in their tails, and this may hint the presence of tail molecular clumps. Indeed, CO emissions are also observed in extraplanar or tail regions of some RPS galaxies, along with H1 or H-alpha. Furthermore, X-ray emissions are detected in some RPS tails, showing evident multiphase nature. To reproduce star formation activities in multiphase tails, we used radiation hydrodynamic simulations in our previous study, Lee et al. 2020. In that study, we imposed varying ram pressure on typical dwarf-sized galaxies, and we could see interesting RPS features. However, we failed to find tail star formation in any cases. This is because no molecular clumps form in the tails for some reason. So we again look into observed cases that have a huge amount of tail molecular gas. So far, less than 10 cases have been reported, and we found that all of them are commonly gas-rich in their disks, experiencing strong ram pressure in the cluster environment. Of course, the number of samples is not enough to say something yet, but we hypothesize that the plenty ISM may play a key role in multiphase tail formation after stripping. If it is the case, then the galaxies in our previous study do not form tail molecular clumps due to the insufficient ISM. Motivated by this, we carried out follow-up simulations using a galaxy of a raised gas fraction, but employing the code and the physics the same to those of Lee et al. 2020. In this study, we used Ramses RT, but let me skip the details of the code because this is Ramses user meeting. The version of Ramses RT we use is the one updated by Harley and Tesson. They implemented a modified photochemistry model into Ramses RT to enable it to trace the formation and destruction of molecular hydrogen. We carried out simulations in idealized circumstances like wind tunnel experiments. We adapt the initial condition generated by Joachim using make disk. The initial stellar mass of the galaxy is 2 times 10 to the 9 solar masses. The reference galaxy has a normal gas fraction as seen in this H1 fraction to stellar mass relation in the local universe. The normal one is marked by the red star here, lying on the mean trend. We made the reference galaxy gas-rich by raising each H1 fraction by a factor of 5, as marked by the blue star. This is thus evidently gas-rich, but likely one in the local universe. And this shows the phase-on and edge-on views of the gas density and temperature of the two galaxies just before encountering ISM winds. Because of high gas density, the gas-rich galaxy has much higher star formation rate, which induces vigorous supernova feedback. So the gas-rich galaxy has a more feathery and thicker disk compared with that of the normal galaxy. In this study, we utilize 3 different simulations. One of them is the normal galaxy experiencing strong ram pressure, which is adapted from our previous study. And we additionally ran 2 simulations for the gas-rich galaxy. First, we ran a no-wind case as a control sample. In another round, we imposed a strong phase-on wind that mimics ram pressure at the cluster center. To trace the metal origin of gas or stars, we purposely neglected the metal yield from supernova in our all simulations. So please see Lee et al. 2020 if you are interested in the impact of varying ram pressure on a typical dwarf-sized galaxy. Then let me show you what happened if the normal galaxy encounters the strong wind. The wind rapidly removes the most gas in the disk, leaving a small core behind. Stripped clouds initially form a tail, but soon almost disappear as blown backward or disrupted by interaction with the hot ICM. For your information, the simulation time starts when the wind is launched in a boundary of a simulation box. In the gas-rich run, you can see much bigger gaseous disk due to strong star formation activities. The strong wind also rapidly truncates the disk, and the tail feature is much evident here. This may be primarily due to the plenty ISM stripped by the strong wind, but it seems that a large amount of cold gas also form in the tail like that. Let me show you the birthplace of stars in the gas-rich galaxy. The top panel is for the no-wind case, and the bottom panel is for the case with strong ram pressure. The x-axis indicates vertical distance from the galactic midplane, and the y-axis indicates radius from the galactic center. The gray shades show the initial locations of stars that form before the wind launch, and the color codes denote the formation epochs of stars stellar particles born after the wind launch. When no ICM winds blow, no stars form in the region of 3 kiloparsec from the galactic midplane after 100 megayear. In contrast, many stars form in the tail region of the gas-rich galaxy, so we assume this distance as the demarcation of disk and tail stars. Most of the tail stars form in the near wake within 10 kiloparsec from the galactic midplane, but several stellar particles also form in the distant tail. We then look into star formation rates of the galaxies in the 3 simulations. In this figure, solid and dashed lines present the star formation rate in the disks and tails respectively, and you can see that the disk star formation rate is quenched over time due to the strong wind compared with the black line, the no wind case. I'm sorry. The decay rates of the disk star formation rates are almost the same to each other between the normal and gas-rich galaxy, and this may indicate that ram pressure can effectively suppress star formation activities in galaxies with any gas fractions at the cluster center. On the other hand, the star formation activities are rather boosted at the center of 2 galaxies due to gas compression by ram pressure. In the tail, only the gas-rich galaxy shows a robust star formation activity after interaction with ram pressure, while temporal and weak star formation is seen in the normal case. The tail star formation indicates the presence of molecular clumps. We can estimate the metal origin of stars from their metallicity, and this figure shows it as a function of the distance from the galactic midplane. In the near wake, as indicated by their ISM fraction, tail stars mainly originate from the stripped ISM. On the other hand, the ISM contribution becomes as important as the ISM in the distant tail stars here. So we wonder if molecular clumps can form in the RPS tail. This figure shows the origin of molecular clouds as a function of the distance from the galactic plane. The colors of the field circles denote cloud density. You can see dense molecular cloud here in the distant tail of the gas-rich galaxy, and we confirm that the dense molecular clumps form and grow in the RPS tail. In contrast, we only found relatively diffuse gas in the tail of the normal galaxy. So we look into the cooling time scale of tail clouds that have ionized fraction higher than 50%. In this figure, the x-axis is the fraction of the ICM, the y-axis is the net cooling time scale, and the color shade denotes the gas mass in each bin. We found that the normal galaxy has much less ionized clouds that can cool and collapse within simulation duration compared with the gas-rich galaxy. Only less than a few percent of those in the gas-rich case. In the gas-rich case, stripped ISM is mixed with ICM and form a large amount of warm ionized gas that can cool within tens of megayear. So one of the take-home messages of this study is that the abundant ISM is stripped and mixed with the ICM, facilitating a gas cooling in RPS tails. We show that a number of stars form in the RPS tail of the gas-rich galaxy. In observations, the presence of such tail stars are mainly traced by HR emissions. So we wonder if HR emissions strongly correlates with young stars in our simulations too. In this slide, you have a dust-obscured HR surface brightness maps at the 2 epochs and the tail star formation rate peaks and the final epoch. The white stars indicate stars younger than 20 megayear, and the gray circles mark stars older than 20 megayear in the tail. The yellow and blue contours show the distribution of entire and young disk stars. As you can see, HRPA emissions are widely distributed in the tail, and we found that the local maxima of HRPA strongly correlates with young stars in the tail. As is done in observations, we estimate the star formation rates from the HRPA surface brightness. In this slide, you see the evolution of intrinsic star formation rates, solid lines, and star formation rates derived from HRPA dashed lines, using the relation taken from BPAS version 2. Very good argument is seen between the intrinsic and derived star formation rate in the disk. In contrast, there is a huge discrepancy in tail here and here. This is because a large fraction of the tail HRPA photons are emitted from diffuse clouds. So, motivated by observations, we apply a limiting flux. For this, we assumed 1 hour exposure of the wide field mode of mu zone reality following some observations. The dotted lines indicate those derived from the HRPA maps with the limiting flux. In the disk, actually no difference is seen between all the red lines because the disk is sufficiently bright in HRPA. On the other hand, most tail HRPA emission is reduced by the limiting flux, and this makes much better agreement between the intrinsic and HRPA derived star formation rates. This result suggests that the tail HRPA luminously may be dominated by diffuse emission, but bright HRPA cores are mostly lit by young stars in both disks and tails. While conducting this study, we found an interesting result reported by Sun et al. 2021. They claim that HRPA surface brightness tightly correlates with X-ray surface brightness in RPS tails. The flux ratio of X-ray to HRPA is measured to be 3.3 on average. They measured the surface brightness on a scale of 10 by 10 square kiloparsec, as illustrated in the figure below above. One interesting thing is that the typical temperature of gas emitting HRPA and X-ray photons is largely different, 10 to the 4 Kelvin versus 10 to the 7 Kelvin. So,
3 more minutes.
Thank you. So, Sun et al. Are saying that this relation strongly suggests the important role of mixing in RPS tails. We also check if this is the case in our simulations. For this, we computed X-ray emissions of the gas-rich galaxy using APEC. You have HRPA and X-ray surface brightness maps at an epoch at which the tail length is comparable with those of some observed cases, for example, D100 in coma or ESO 3701 in normal cluster. From these maps, we measured X-ray and HRPA surface brightness at randomly chosen position. This is not dust obscured. When the X-ray and HRPA surface brightness measured on the scale of 10 by 10 square kiloparsec in the tail, you can see nice agreement between our model and the empirical feed of Sun et al. Here, the dashed line. The color of each dot indicates an averaged ISM fraction in each measurement region. Sun et al. Also find the relation in the disk, the dotted line, and we also measured it from our simulations too. Agreement is also good, as you can see, but when you measure it using much smaller pixels, for example, 0.0 by 0.0 square kiloparsec, the correlation deviates from the empirical fit, and the separation between the disk and tail is less clear. And HRPA is brighter in the pixels with a higher ISM fraction, that is when the dots is getting redder from left to right, because the main source of HRPA is warm ionized gas, stripped ISM. This shows that the correlation found by Sun et al. Is partially formed due to their measurement scale, because a large measurement scale summated emission coming from clouds of different conditions. But the X-ray to HRPA ratio ranges from 1 to 10 in the tail, which is higher than that in the disk and much lower than that in the ICM. So even though the flux ratio is changed over different measurement scale, our results still support the interpretation of Sun et al. This is summary. As an important result of this study is that the ICM-ISM mixing plays a critical role in the development of multi-phase tails. Molecular clumps can be formed in the RPS tail in situ with efficient cooling facilitated by mixing. Thank you.
Thank you very much for this talk. Questions? Yeah, I have one, but let's start with Martin.
Yeah, thank you, Jaehyun. It's really interesting. So I'm not entirely clear about what your setup is. So what you do is you have the galaxy sitting in a box, and then you turn on the wind after a certain amount of time, and the wind is kind of constant density and speed. But is that really what happens when a galaxy falls in a cluster? Don't you expect some kind of buildup of both of the ram pressure effect that maybe compresses the ISM of the galaxy before it starts stripping it, and so on and so forth?
Yeah, but that's very good question. I think that's almost a comment. And there is our future plan. So put a galaxy in a live halo and see what happens if there is a real gradually increasing ram pressure and real, how can I say, the tidal field. Yes. I think that may make different result.
Cool, because that might actually be a way to achieve more gas rate fraction if you start by compressing the ISM.
Yeah. So gradually increasing ram pressure may gradually decreasing the gas fraction.
Thank you.
Okay, Francesco.
Yeah, sorry, maybe somewhat related with what was just asked. Did I understand well? Do you also observe a boost of the star formation somewhere or not?
Yeah, at the center, yes. At the center, yes. When we impose mild winds, okay, towards the galaxy, then the overall star formation rate is rather immense. Of course, the boosting star formation is mainly concentrated at the center because at the central region, the resilient, the how can I say, the gravitational potential or the self, so the kind of pressure exerted by supernovae can sustain the structure. So the star formation tend to be boosted at the center.
Enhanced the stuff. But
yeah.
How much? By how much?
I'm sorry, by how much?
By how much? Could you quantify? By
yeah. On average, how can I say, up to 50% with the mild wind.
I see. Thanks a lot.
You can find some exact numbers in our previous study.
Okay, thanks.
Okay, Yuan.
Thank you for the nice talk. There are some papers in the literature looking at the effect of thermal conduction. I think about the papers by Armilota and Fraternali in particular, which show the important role of thermal conduction for the interface between the 10 to the 4K gas and the corona, the CGM, in setting the evolution of the cold gas. I mean, do you think this will affect strongly the amount of gas and star formation in the tail in your simulations?
So are you saying that the thermal conduction can affect the cold gas phase in the Ramses strip cloud? So I think I may miss your point.
So thermal conduction will temper the amount of gas that can condensate in the tail in principle. But I'd like to have your opinion on this.
I didn't check that, but there is a kind of reference about that. Thomas and Brian. Anyway, Thomas's paper in 2015. Anyway, she said that the thermal conduction plays an important role in tidal tail. I'm sorry, the Ramses strip tails, so they don't play any significant role.
Jaehyun, if I may barge in, I think Johan has a point that thermal conduction could be an issue. So that's our next project.
Yeah, thermal conduction. Yeah, but you're right. But at the same time, you're right. Yeah.
Okay, we are running a bit short on time for the break, but I will let Julianne in because you had a hand up for a while, and then we'll break. Okay.
Hi, Jaehyun. Thanks for a very nice talk. So my question was like a little bit similar to Johan's, in the sense that I was wondering what you thought would change if you added magnetic fields to the simulation, right? So would that impact the thermal conduction and therefore the condensation of the gas in the tail, or would that change the morphology of the tail? I wanted you to comment on this. Thanks.
There are some references, and I'm not sure actually, but overall, I think from the references, I think magnetic field will make less clumpy structures in the tail, but at the same time, I heard from Tesson that magnetic field will how can I say, will stabilize the disk structure and rather enhancing star formation, but I'm not sure. So that is our the future study.
Okay, actually, so Jinsu, you had your hand up for a while, so let's go for the last question from you, and then we'll go for the break.
Thank you for giving the last questions. I have some more questions. Thank you for your nice talk. I'm wondering whether in the weak wind case, the stripping gas can be reinforced to the galaxy or not.
I'm sorry, the weak wind case? Relatively much mild wind case. I'm not sure if that was that weak, but when we ran a mild wind case, or even weak wind case, we couldn't see any prominent reinforced gas, because anyway, the ISM wind is the pressure of the ramp pressure is the ISM wind is much stronger than such that reinforced. I think I saw that kind of thing from a set of a simulation, but it depends on the kinematic status of the galaxy. But you can expect that kind of thing, but in general, the ramp pressure is much stronger than the reinforced.
Okay, we can discuss it in the coffee room.
Yeah.
Tesson looks quite unhappy. I'm sorry.
Yeah. Actually, yeah, we can continue discussing this during the coffee break, but I will officially announce that we should stretch our legs and get a cup of coffee, and that we will come back at 11:10 for the next talk. Okay, so let's break for now, but please stay and chat the coffee break.